dotted with dr dt dt. Now how can I rewrite this as an integral of some function times speed? How can you could do this, right? This is really the integral from a to b. Now the speed we can rewrite as what? Remember, it's been a while, but you can rewrite this as the magnitude of dr dt times the unit vector that points in the tangential direction. Remember our notation for that? Big T, the unit tangent, right? Speed times the direction of the speed, the direction of the velocity. So this is really just f dot the unit tangent, right, times this dr dt. Or, going back to yesterday's notation, this is the integral over the curve of f dot t ds. I mean, we should always remember that the speed works out to what? ds dt, right? So I mean, yeah.
It's still a function of r of t, right? That hasn't changed at all.
Yeah, I mean, to be more technically correct here, this is fine. F of r of t dot t of t. Ugly. But that is f dot t integrated. It's the arc length integral of f dot t. What is f dot t? You could call it f sub t. It's the tangential component of f, right? To give a a kind of very easy to calculate example that's kind of based on this. How about the force is the magnetic force, Q V cross B, right? This is the magnetic force on a charge Q with velocity V subject to a magnetic field B. The magnetic force is perpendicular to the velocity. This is the force law. So if you calculate the work done by the magnetic force along some curve, you get 0. Because the tangential component of f, which is QV cross B, is 0. Right? I mean, if you don't believe me, f dot t is f dot, well, it's q v cross b dot product with v over v, right? V over v is t. Take the velocity, divide by the speed, that's the unit tangent. What's the dot product of a cross product where, one of the vectors is being crossed? Is the same as that v cross b is perpendicular to v, right? This is 0. So this is why magnetic forces can do no work. They're perpendicular. I wouldn't say they're conservative. I'm not going to about that. Anyway, they can change the direction of the velocity, but they can't change the speed. Okay, so there's that. Now, let's get back to the question of coordinate change, right? what happens if we study a reparameterization? I keep losing my mark. Ah, thank you. Of that list of 4 things, the one that's probably the most difficult to prove is that path independent implies conservative. The direct proof of that is interesting and non-trivial. So of course I will do that tomorrow. The idea is we're going to do the most complicated thing we can think of for the CFAWs. That was the idea. Okay, so suppose, excuse me, oh goodness gracious, I'm sorry. A1 to B1 of f of R1 of t dot dr1 dt. So this would be the work set up along one parameterization of the curve, okay? So let's see, we can change this. I want to say what? R1 of t is equal to R2 of what? Of u of t. And u of A1 is equal to A2. U of B1 is equal to B2, right? So let's see here. This becomes what? A1 to A2, f of R2 of u of t dot dr1 dt. So what would dr1 dt be if this is the relation between the 2 parameterizations? What's dr1 dt in terms of dr2? It's it's times du dt, right, by the chain rule? So the chain rule pops out a du dt here, right? Yep. Oh, yeah, sorry. Follow man. Oh, yeah, that's on purpose. So all I've done so far is just converted with the reparameterization. But now I'm going to change the integral. I'm the u substitution that goes from what to what? This goes from A2 to B2. And then this is f of R2 of u dotted with dr2 dt. I mean, technically, I should really write this dr2 du. That'd be a better notation there. Same for this, because our dr2 is evaluated at u of t, so I can write that as dr2 du. Yes, sorry. The point is that this is, again, the work done, but in the other what's the word? Words. Other path, the other parameterization of the curve. Now, I have assumed something about the bounds when I wrote this. What does this assume? I mean, if these are 2 likewise, I'm assuming that these are both, if I assume this, I'm assuming that both of the paths have the same orientation. So this really assumes that du dt is greater than 0. In other words, that gamma 1 and gamma 2 are both both paths. So here's the curve, right? And so gamma 1 and gamma 2, listen to me, R1 and R2 and R2. They're both going from, R1 of A1 is equal to R2 of A2, and R1 of B1 is equal to R2 of B2. If they were reversed, then the U of t would be negative, right? So if I, oh goodness gracious, I'm running low on energy today, guys. I'm kind of sick. What I'm trying to get across to you is I only get equality here if both of the paths have the same direction. If one of the paths was reversed, right? If it went from, if it was from point P to point Q versus, I give this a name. Say this is point P. Say this is point Q. So if I instead had my second parameterization going from Q to P, then the bounds would get, there would be a minus because I would have to flip the bounds in order to have the right kind of integration to define the integral. So in other words, we can argue, and I think it's a little bit more clear in my notes, by the way, guys. If you don't understand what I just said, look in the notes. There is a pretty clear argument there. So this is minus the integral of c of f dot dr. This is a property of the line integral. If you reverse the curve, it introduces a minus. Now, some of you should feel some sense of you should be a little bit disconcerted, because last time we showed that f ds was integral of f ds. Whether I look at the curve or its reversal, I get the same, I get the same sign, right? So the integral with respect to arc length is much more like a double integral. We just add up things. We don't have any sense of direction, whereas the line integral very much cares about the direction of the curve. Yes, Mr. Gibson.
Because the vectors involved are going in different directions relative to the direction of travel on the path.
That's exactly why, right? Because if you think about C, if f looked like this, right? So if the original path had these sorts of tangent vectors, right? Then the reversal has exactly the opposite tangent vectors, so everywhere it's minus what it was. So yeah, we introduce a minus when we reverse the curve because exactly f dot t is opposite. But some students inevitably get confused over this point. Like, wait a minute, you just wrote this, you just told me this is an arc length integral though. And you've also told me yesterday that the arc length integral doesn't care about orientation, so how can we have both of these things? How can it be that this is an integration which is independent of the reversal of the curve, and yet when I reverse the line integral, the curve of the line integral, I get a minus? How can these both be? Yeah. Say again? After I take the dot product, I get a scalar. That's true. Can you elaborate on that?
And then it's just a scalar function, which doesn't care which direction.
So your point is that's right. That innocent-looking little f over here, we assume that this f has nothing to do with the curve C. This, quote-unquote, f is not an innocent bystander with regards to the curve. That is very much tied to the curve, right? When you reverse the curve, you reverse the t. So that's why you'd still get a minus from the scalar integral when you reverse the curve, because the function that you're integrating over with respect to arc length is not independent of the curve. In fact, it reverses, it changes by a sign. And that's the reason for the mystery. So tomorrow, I will show you the fundamental theorem of calculus for line integrals, and we will prove that conservative forces conserve energy, and hopefully we will show that you can build a potential energy function for a path-independent force. That's my plan. Thanks, guys.